We want to talk about the knapsack problem. And you may have heard about this problem before, but let's briefly reintroduce it. In the knapsack problem, we are given n objects, and each of those objects or items has a value and a weight, and both of these are positive values. We also have a knapsack that has a weight constraint of, say, capital W. Now, the goal is to select a subset of our objects in such a way that that subset, if we sum up all their weights, they don't violate the constraint of our knapsack. So we could put them all in the knapsack without the knapsack breaking. And ideally, we want to select a subset of objects that doesn't violate the weight constraint, while at the same time maximize the total value that we can pack into the knapsack. So here's a simple example. We have 5 items, and their values are 1, 6, 18, 22, and 28. And their respective weights are 1, 2, 5, 6, and 7. And suppose we have a knapsack with a weight limit of 11. Then it would not be possible, for example, to fit item 3 and item 5 into the knapsack at the same time, because item 3 weighs 5 and item 5 weighs 7, so together they have a weight of 12, which exceeds our threshold. We could, however, fit, say, item 2 and item 5, because together they weigh only 9, so they would fit into the knapsack without any problems, and they would give us a total profit of 6 plus 28, so 34 in total. But we can do even better. So for example, we could pick item number 3 and item number 4. Together their weight is 11, which just about fits into the knapsack, and the total profit we would get is 18 plus 22, so the profit is 40. Much better than the 34 we had before. And in fact, I think packing item 3 and item 4 in this example is the optimal solution. We can formulate a decision version of this knapsack problem by having all the same inputs we had before, plus in addition to this, a target value, capital V. And now the yes or no question we would ask is it possible to find a subset of the items such that that subset fits into the knapsack without exceeding the weight threshold, capital W, but such that that subset has a total value of at least capital V. This decision problem is NP complete. It's quite straightforward to see that it's contained in NP because we can just give the subset of the items that we claim to have this particular property, and then a certifier could check that indeed all those items fit into the knapsack, don't exceed the weight threshold, and their total value is also large enough. To see that the knapsack problem, or the decision version of the knapsack problem, is complete for the class NP, we can use a polynomial time carp reduction from subset sum. As a reminder, in subset sum, we are given a set of non-negative values and a target integer, capital U. And the question is, if there's a subset of those values such that the values in those subsets sum up to exactly the target value, capital U. If we get an input for such a subset sum problem, then we can transform it into an input for the knapsack problem in the following way. We set the values and the weights of all the objects in the knapsack problem to be equal to one another and equal to each of the numbers of the input to the subset sum problem. So the number of objects we would create for our knapsack problem would be equal to the number of numbers that we have in the set for the subset sum problem. The weight limit of our knapsack would be set equal to capital U, the target value we want to hit with our subset for subset sum. And the value you want to achieve in your knapsack problem will also be set to this capital U. And if you think about what knapsack is asking for now, it's really asking for a subset of items such that if I sum up the weights of those items, the weight will be at most capital U. And if I sum up the values of those items, it will be at least capital U. But the weights and the values are just the same and are just the UI values from the subset sum problem. So really, we have an inequality in both directions, which means the only way to satisfy this is to have equality. So in this case, we're really asking, is there a subset such that we exactly reach value or weight capital U? And that's exactly the same condition we have in the question for the subset sum problem. So this is a valid reduction. If you write this down, you probably have to be a bit more formal about it, but I think this conveys the main idea and should be enough for now.